Hi everybody, welcome back. So what I've done is I've added another element for us to calculate. I have given us a source voltage of 120 volts. So what we are going to do now is I want to look at what is the current, what is the total circuit current of what we have here. So we know that Ohm's law says that my total circuit current is going to be derived from my total EMF divided by my total impedance of my circuit. So I have an EMF of 120 volts. I should have elaborated. We're going to leave this with rectangular form. So with rectangular form, I need to know what I'm going to use as my reference because it's important to know where these things are going to fall within relation to one another. So 120 volts, we're going to use my source voltage as my reference. Why? Because it's my constant. I can mess with this circuit as much as I want. 120 volts, that's not going to change. I can add components, I can remove components, I can short circuit components, I can burn out components. Current's going to go all over the place. What's going to stay the same? An EMF. That's why we make it a reference. So I have 120 volts as my EMF divided by, and what I want to do first of all is I want to leave it in rectangular form. So, and this is going to help us eliminate steps, okay? It's also going to help us eliminate points of error and accuracy problems. If I just take 15.62, when you calculated this impedance, you would have probably seen this was like 10 digits long, the decimal points. So if I just carry over 2, I'm now losing a point of accuracy. So if we're trying to be as accurate as possible, given our parameters, I know if you're thinking about significant figures, technically I can only go to 1. We're going to leave it. We want to carry as much values forward as possible. So really, I want to go back to where I have this in rectangular form as 12 plus I10. And I'm going to use that value because when I calculate this, what it's going to do is it's going to give me a very distinct value of where this falls. So what you'll see is you'll notice that, now if you have a graphing calculator, if you have a calculator that you have to cycle between the x and y components and my radius and theta, you might have to, but what I want you to see is how they all correlate together. It's just important to understand what the tool I'm using, so the calculator I'm using, how it's computing that. But what I end up with is I end up with I'm going to round pretty heavily, 5.9 minus I of 4.9. And you might look at that and says, how on earth is that a current, Jason? So what this is my rectangular form of current. I have 5.9 as my in-phase value, and I have an imaginary value of 4.9, or an out-of-phase component of 4.9. And if you'll notice this minus symbol, that makes sense because this is an inductive circuit. So my reactive component is lagging, it's minus, it is behind my voltage. That's exactly what should happen. In an inductive circuit, my reactive current is lagging my in-phase current. That's why this minus sign shows up. Perfect. That's exactly what should happen. Now, if I wanted to know a total value, you could plug this into your calculator. You could ask your calculator to convert it into a polar function, or I could just compute this, and I end up with a total circuit current of about, sorry, that's a little bit messy, 7.68 amps would be my total circuit current. So that's, if you were asked for what my total circuit current, this is what you would want. But it's good to actually see where this rectangular function falls and how this will end up displaying that. The great thing about this is if I wanted to ask, or I wanted to know what the power of this circuit, what the real power of this circuit, it's coming from my 5.9 amps of active current. If I wanted to know my quadrature power, well, it's coming from the 4.9 of my vertical axis, or my imaginary current, my out of phase current. Those two values are very, very important for us. So this is just rectangular form and how we can use some of those values. You'll notice there's no angles here. There shouldn't be. This is rectangular form. There are no angles with rectangular form. When the next few videos will be about polar form, that'll get us into some of the angles. I can still evaluate my lead and lag. There is no leading component, but my lagging component's in this circuit because it shows up in that rectangular form when I do my calculation. So I hope this has helped. If you've got any questions, feel free to shout out. If not, we'll see you in the next one.